Hello and welcome to online platform of Wacom College. And in this today's lecture, we starting the concept of transistor or introduction to transistor. So before starting to transistor, we going to learn the first what is meant by the semiconductor, types of the semiconductor, that is intrinsic type and extrinsic type of semiconductor. Next one is formation of the p-n junction and the devices of semiconductor, and after that we learning the what is meant by the introduction of the transistor. Once you understand the semiconductor, formation of the p-n junction, so we can easily understand the structure of the transistor and working of the transistor. So any material, solid material, is divided into three types: conductor, insulator, and semiconductor. Depends on its resistivity property. So if the material have low resistance, that means the current can easily flow from this material. So this material is nothing but the conductor. So examples of the conductor are the aluminum, copper, gold. So these are the example of the conductor. If you use this material and you apply the voltage to this material, the current easily flow from this material. The next type of the materials are the insulator. It have the high resistivity. That means its conductivity is very low. Please note that the resistivity and conductivity both are the inversely proportional to each other. If the resistivity is increases, conductivity is decreases. So when the insulator is used, so it's have the high resistance, that means conductivity is very low, so current cannot be flow from this material. And third types of the material is nothing but the semiconductor. So these semiconductor have the resistivity or conductivity is lies in between the conductor and the insulator. So an example of the semiconductor materials are nothing but the silicon and the germanium. So these are the common material used in the semiconductors. Apart from this silicon and germanium, there are also other semiconductor materials. But these are the famous and most usually material silicon. So in this graphical or pictorial form, the conductivity of the insulator and semiconductor and insulator is shown. So these notations is nothing but the conductance inversely proportional to the resistance. If you use here resistance, there is only ohms unit symbol, and this ohms inverse is nothing but the unit of the conductor. So we can look the insulator have the 10 raised to minus 18 conductivity. That means conductivity is very less, very small, and conductivity is inversely proportional to the resistivity. That means the conductivity is very low, the resistance is very high, so high resistance for the insulator. Next one is a conductor. So conductor has shown 10 raised to 18. That means this value is so much high, that is the conductor have more conductivity. That means conductivity is very high, so resistance is very low. And in between the conductor and insulator, this is a third material, that is semiconductor, whose resistivity is lies in between the 10 raised to minus 8 to the 10 raised to minus 6. So these are the some commonly used semiconductor material in the group of the four: silicon and germanium. And if you use this material along with this material, that is column third and fifth combination, so we can be obtain the semiconductor materials. If you use column 4 and 3 in combination with this silicon material, we can be obtain the compound semiconductor. So if you use only this silicon and germanium, these are the single semiconductor material, and if you make some mixing, that is doping concept, with the column of the fifth or column of the third, so these material are nothing but the compound semiconductors. So generally used semiconductor material is the silicon, which have the atomic number of the 14. So this atomic number of 14 is divided into the levels or orbits, which have the first orbit full, that is a 2 electron in the first orbit. Now next one is a 8 electron in the second orbit, and next one is a 4 electron in the last orbit. So remember that the silicon which have the electron in the last orbit are the 4. So that means it can be give the electron, or it can be take the electron. To make the stable is last electron. So any atom is trying to make it stable by completing its last orbit. So it can be trying to give the electron, it can be try to accept the electron. So like that, the silicon, that is have the 14 atomic number and 4 last valence electron. Similarly, there is another material, that is germanium, that is which have atomic number of the 32. First orbit 2 electron, second orbit have the 8 electron, next orbit has the 18 electron, and again last orbit consists of the 4 electron. That is the same property. Look at the basic structure of the silicon. So this is silicon, and these are the 4 outermost electron. This is the 4 outermost electron, and when this semiconductor material crystals form, so they try to make stable by sharing its electron. So this is a one single silicon atom, and it shares its 1 electron to the neighbor. That means here look, this is a 1 electron of this silicon, and this 1 electron of this electron. So they form the one pairing of the bond. So they form the bond. So this is nothing but the covalent bonding. So this is a covalent bonding. So this is a covalent bonding. So any semiconductor material, especially for the silicon and germanium, we can look the such type of the covalent bonding. So next one is electrons property of the silicon, and this property, we generally speaking, for the resistivity. And any material, the resistivity is changed. This resistivity is changed. Electrical resistivity is changed because of the charge carrier. So in silicon or in semiconductor, there are the 2 types of the charge carrier. There are the 2 types of the charge carrier. One is a conduction electrons, and second one is a holes. So because changing the number of the electrons or holes, the resistivity property of the silicon can be changed. And how we can change this property of the silicon, that is a semiconductor resistivity of this material, by this 4 process. One is by adding external atoms, that is nothing but the doping process. By adding the special impurity atoms in the semiconductor, this process is nothing but the doping. So when you add some external atoms, the resistivity of this semiconductor can be changed. So depends on that there are the 2 types of the semiconductors, that is a P type and the N types. So again, next one is we can change the resistivity of the semiconductor by applying the electric fields. Third process, we can change the electric property of the silicon by increasing the temperature or decreasing the temperature. And third is by some radiation. If you apply some radiations, so the property of the semiconductor can be changed. Next concept in the semiconductor is the electron-hole pair interaction or the generation. So before going further this time T1, T2 and T3, I showed here the concepts of the electron and hole pairs. So in this first, we can look, this is a covalent bonding is formed between this silicon and this silicon by sharing of the 1 electron of this silicon here and 1 electron of this silicon here. So these 2 electrons are shared by these 2 silicon and form the bond, that is a covalent bond. But if one of electron is left from this pair, that is the 1 electron is left from this pair, so there is a creation of the holes. So that is nothing but the hole, and here is a extra one electron. So this is nothing but the creation of the electron hole pair. If this electron goes again this hole, this electron will be vanished, and this is again there is a creation of the electron here. But if there is a lack of the electron in this covalent bond, this lack of electron is nothing but the hole. Actually there is a nothing concept of the hole, but this is a word that is shows there is a deficiency or the lack of the electron. So again we can look at this some timing process. At consider time t is equal to 1. So there is a one hole, that means there is a one deficiency of the electron. There is a need of the one electron to complete covalent between this silicon and this silicon. So if this silicon obtain one electron from this pair, so this electron goes to here and complete bonding or covalent between this silicon. So look at here. So this electron goes here. That means what happened? They complete his covalent bonding, but there is a lack of one electron. So this is nothing but the creation of the hole. Again, suppose this pair one electron is knock out, म्हणजे बाहेर जर पडला आणि तो काय झाला या ठिकाणी येऊन बसला तर काय होणार आहे? So these two silicon completes his covalent bonding and there is a one deficiency of the electron. That is nothing but the hole. So we can look here generation of the hole. So in that way there is a electron hole pair are created. Next one, type of the semiconductor. So first one is intrinsic type of semiconductor and second is the extrinsic type of the semiconductor. Intrinsic type of semiconductor are nothing but the pure form of the semiconductor. So this is the intrinsic type of the semiconductor. This is a perfect semiconductor crystal with no impurities or lattice defects. It's called as the intrinsic type of the semiconductor. That means all the atoms are uniformly of the same material, that is silicon to silicon. If this is a crystal of the germanium, there is all atom of the germanium. There is no other type of the atom. So these are all other silicons. So this type of the semiconductor is nothing but the intrinsic type of the semiconductor. And here are the number of the electron and number of the holes are the same. There is no extra holes and electrons. Number of the electrons and number of the holes are the same. The drawback of this type of the pure type of semiconductor is that we cannot be change its electric property. So that is the drawback of this intrinsic type of the semiconductor. The next type of semiconductor, that is extrinsic type of semiconductor. So drawback of the intrinsic type of semiconductor is that its electric property which cannot be changed. So if you add some external impurities or some atom in the pure form of the semiconductor, so the resultant semiconductor is nothing but the extrinsic type of semiconductor. And depending on the doping atom or impurities, there are the two type of the extrinsic type of semiconductor, namely N-type semiconductor and second one is the P-type semiconductor. Now if you look the P-type semiconductor, the addition of trivalent impurities such as boron, aluminum or gallium to an intrinsic type of semiconductor, that is pure form of semiconductor, will create the hole. So you can look here in the picture form. Here is a silicon that is pure form and have 4 valence electrons or last orbit electron, and if you add column third impurities like the boron, aluminum or the gallium, here we add the boron, and in the boron they have the last orbit 3 electrons, and the resultant bonding structure we can look in this picture, that this boron form the 3 covalent bond with the neighboring silicon, this first, this second, this is the third, and the fourth covalent bond is cannot be formed and there is a one missing electron. So this missing one electron we can be says that this is a hole. So in case of the p-type semiconductor, and we add the impurity, the resulting we get the structure in which there are the majority charge carrier are nothing but the holes, because there is a one deficiency of electron. So this type of the semiconductor is nothing but the p-type semiconductor. Again, if you look for the n-type semiconductor, and if you add the pentavalent impurities, the pentavalent impurity is nothing but in which last orbit contains the 5 electron. And which are these elements, atoms? These are nothing but the antimony, arsenic, or the phosphorus. If you take the phosphorus, which have the atomic number of the 15, that means the first orbit have the 2 electrons, second orbit have the 8 electron, and the last orbit have the 5 electron. So for this example, we have taken the arsenics, and in arsenics there are the 5 electron in the last orbit. So arsenic forms the 4 covalent bond with the neighboring silicons, first, second bond, third bond, and the fourth pad, and 1 electron is remain as it is. So this extra electron we get in the p-type silicon. So that means if you take the p-type semiconductor, so p-type have the extra electrons, that is nothing but the majority charge carrier are nothing but the electrons. So that much for the today's lecture. In next lecture we learning the what is mean by the p-n junction, and how the depletion layer created, and how the diode is created. Okay, thank you.